Hello, and welcome to the Scientific Adventures of Beardman. As we begin our year in physics here, I'm not sure what you're hoping to accomplish. Maybe you're someday hoping to build bridges, or maybe you just want to learn how to hit the baseball better, or the softball, or throw a better pass, or tackle more effectively, or spin better in a dance move. Whatever it might be, the physics that you're going to learn here can help you to do that. But before we can do that, we have to begin by developing a model that will help us to describe how things move. From there, we'll get to the idea, what causes them to move and so forth. But right now, what we have to do is be able to describe how things move in an effective way, in a numeric way. To that end, we're going to describe three basic concepts: the ideas of distance or displacement, the idea of speed or velocity, and the idea of acceleration. If you've been following away with the order that I set up this course, you've already watched the concept builder for distance and displacement, so you have an idea of that, as well as most people kind of already know what distance is. So I'm not going to spend time on that. Here's a link to that video if you would like to review it. So now, on to speed and velocity. Now, most people do have a basic idea of speed or velocity because at some point in time, you or somebody driving a car you were in may have been pulled over by a law enforcement officer to give you a ticket because you were exceeding the speed limit. Yes, so you have a basic concept of what speed is, a certain number of miles you travel in an hour. Now, as we talk about speed and velocity, those two are slightly different. Speed is a scalar, velocity is a vector. But for our purposes, because we're dealing with one-dimensional motion, things moving in a straight line primarily, we can just kind of talk about speed and velocity as the same thing. So if you're doing other stuff, two-dimensional stuff, you will want to go deeper than this. So speed is the rate at which your position is changing. The amount that the position changes is the displacement. And like I mentioned, distance and displacement, we're going to kind of treat as the same thing because we're dealing with one-dimensional motion. So the next question is, what is a rate? If speed is the rate at which position changes. Well, a rate is how much something changes in a certain amount of time. Of course, you're most familiar with how many miles you can go in an hour, or depending on the country you're in, how many kilometers you can travel in an hour. But we're going to use different units in the classroom. We're going to use how many meters can you go in 1 second. The reason for that is twofold. Primarily because we use the MKS metric system in physics, at least in high school physics. Not necessarily particle physics, but in high school physics, which means meters, kilograms, and seconds. So if we measure everything in meters per second, in meters and seconds, and get speeds and velocities in meters per second, then when we go on and calculate forces, we'll get the unit newtons. When we calculate energy, we'll get joules, pressure, pascals, etc. Secondly, and not quite as important, but it's reasonable, is that in our lab, we will not be walking for miles and measuring how many hours it takes. Instead, we'll walk a distance of meters and we'll measure with a stopwatch how many seconds it took. Like anyone uses an old school stopwatch anymore, you're using a phone, right? Start, stop, there you go. So, as we were saying, when we measure speed, we're measuring the rate at which something is changing, how much it changes each second. To turn that rate into an equation, we're going to take our change in something, change in position, and divide it by time. Okay? And so that would technically give us displacement divided by time, or because we're doing one-dimensional motion, distance divided by time will be the same for the one-dimensional motion portion of it. And so that's going to give us actually distance divided by time gives us average speed, and displacement divided by time gives us average velocity. But like we said, one-dimensional motion, it's all the same. The equation that you'll see if you're here in the state of California on your standardized test, on the formula sheet, you'll see S equals delta D over delta T. Okay, if you're somewhere else or using a different physics textbook, you might see v equals d over t or v equals delta x over t. All those are fine. They get the basic idea. Yes, we're going somewhere. However far we go, it's divided by the time. First, I want to talk about why you sometimes see something over delta t and sometimes you see something over t. Well, technically you are seeing over delta t. That's what it should be, okay? Because you're seeing a change in time. Because time itself is like 2010, May 2nd, at 10:27 p.m. and 23.87 centiseconds. Anyways, that would be a time, an absolute time. That's the time. And anytime we talk about the length of time something takes, that's really a change in time from 10:27 to 10:27 and 30 seconds is a time of 30 seconds. Well, it's really a change in time of 30 seconds, but we'll just call that a time. Most people do. You don't say, how much change in time should I bake the cake? You say, how much time do I bake the cake for? Okay? And so, even though it's technically a change in time, because we so commonly use the word time to mean a change in time, often you'll just see the equation as delta v over t, at the high school level especially, okay? And maybe an algebra-based college course or something like that. So it's perfectly acceptable if you want to just kind of ignore the delta and just think of it as the time. A quick side note, many of you, and in my course, you will go and you will be graphing motion of things. You'll be doing position versus time, velocity versus time, acceleration versus time graphs, and the time that's going to go on the x-axis is actually an absolute time. We don't put the year and the date and all that in there. We just count the time when we started the stopwatch. There I am using an old school stopwatch again. We count the moment we hit the stopwatch as our absolute time of 0. And then the other numbers are absolute times based on that time being 0. Now, for us Californians, I like a lot of what we do here in California, but I do not like that they chose to use delta D in the numerator here. Those of you that use D or delta X, excellent, that's great. But delta D, the change in the distance, what does that even mean? I guess if you're comparing it to some absolute original position, then your change in your distance from that original position is really the change in your position. So it really should be delta X. Or if you really want to do delta P, but pretty much everyone uses position as X, especially in one-dimensional motion. So delta X would be much better. We're really talking about the distance here, so delta D, once again, in this case, you ignore the delta. It should be delta X, and then you pay attention to it, or it should be D, and that would be a much better way to describe it. So now, ignoring all those little idiosyncrasies of the delta D and the delta T, the basic idea is that we're taking how far we go, the distance, and we divide it by the time, and that gives us our average velocity. Okay? So for example, Usain Bolt ran the 100-meter dash in 9.58 seconds for a world record. And so if we plug in for our distance, 100 meters, and we plug in for our time, 9.58 seconds, we can divide the two and calculate that Usain Bolt, on average, for his race, was running 10.4 meters per second. Now, this calculation allows us to calculate the average speed or average velocity during Mr. Bolt's race. But we all know he wasn't going that speed the entire time. In fact, he would be cheating if he did, because they are required to stopped. That's weird. They start at a standstill. They start at 0 meters per second. And when the gun goes off, they start a race by shooting a gun. Usain Bolt takes off and starts running, increasing his speed as he goes along. Now, this average speed that we calculate is very useful for a lot of things. It's very helpful to know the average speed of something. Google uses that to figure out how much time it's going to take us to get to where we're going when we use our maps on our phones. But it's not always accurate in the instant because Mr. Bolt keeps changing his speed, and we might want to know what's his speed at any particular given moment. And the speed at a moment like that, we might say the speed at an instant like that, and I could be saying velocity also for our course. The velocity at an instant is called the instantaneous speed or the instantaneous velocity. Now, all the exciting motions that you might want to analyze do not have a constant velocity. If they're just moving along at a constant velocity, it's pretty boring. So fortunately, in this course, we're going to go deeper than just things going at a constant velocity. Like Mr. Bolt, we're going to deal with things that are changing their velocities. And so to understand something that's changing their velocities, we now get to our term acceleration, which is the rate of the change of position. Okay, that got a little wild there. Okay, you ready for that? A rate of the change in position. Well, the rate of the change of position is the speed, so acceleration is the rate of the change of the speed. Okay, or the rate of the change of the velocity more accurately. Okay, but once again, for one-dimensional motion, they're the same. So now that we're trying to understand this rate of a rate, let's just back up a moment and take a look at some examples. Acceleration is going to help us understand how you feel when you're in a car. When you're in a car and you're driving along the freeway at 75 miles an hour or whatever you're going, whatever the speed limit in your town is, do not exceed the posted speed limit. It is dangerous. So you're going along at the speed limit and you don't feel anything. You don't feel pressed into your seat or anything else. You just are going along. It's almost as though you were stopped. Why is that? Well, because acceleration is where we feel things, when our velocity is changing. So when we're sitting at a stoplight and the light turns green and the person driving hits the gas, the harder they hit that gas, the more we're pressed back into our seat. Okay? When they hit the brakes, we feel ourselves lurching forward. And because acceleration is a change in velocity, and velocity is a vector, it includes direction, when they turn the steering wheel, we feel ourselves lurching from one side to the other. Now, a couple things about that. First, notice that whatever direction the car is accelerating, your body kind of feels pushed the other way. Pushed isn't the right word. We'll talk about that later. When you're accelerating forward, the gas pedal at the red light, your body kind of feels like it's going back. When you hit the brakes, the car is accelerating to stop, and your body feels like it's going forward. And when you turn left, your body goes right. When you turn right, your body goes left. What is that? What's going on? Well, when the car accelerates, your body has to accelerate too. And so, what's going to cause your body to accelerate? The car, some part of the car is going to push on your body to make it accelerate. And in other words, your body is, you might even say it takes a little bit for your body to catch up. The car starts going, and then all of a sudden your body starts going. Okay, not quite that lurchy, but you get the idea. Okay, but we'll get more to that when we get to Newton's laws and we get to forces that cause the acceleration. Then we'll look more deeply at like why your body is feeling those different things. One more thing to think about here as you're thinking about acceleration, you can think about it as the needle on your speedometer. Okay, or if you don't have a needle, then the digital readout. But your speedometer changes by a certain amount each second when you're hitting the gas. And when you're hitting the brake, it changes by a certain amount each second. And we'll talk about the turning issue later. Okay, but it's how many miles per hour is it changing each second. In fact, this is how they try and sell you a car, right? This car can go from 0 to 60 in 8.4 seconds. Okay, or, well, that's a bit. But anyways, you get the idea. In a certain amount of time, certain number of seconds. So they're giving you kind of all the pieces of the acceleration, how much the velocity changes and how much time it takes for that to happen. But now, of course, we aren't going to use miles per hour per second, because that would be a confusing unit and not one that's going to help us. Like we said, we want to always be using meters and seconds. So we're going to talk about how much your velocity, your meters per second, change each second. So meters per second, since there's 2 seconds there in the denominator, we can say meters per second squared. Some physics resources you'll see meters per second more often, which is more intuitive. Others you'll see meters per second squared, which is kind of more mathematically accurate, the way to write it. And so now let's take a look at the equation. The equation that'll help you calculate acceleration is change in velocity divided by the change in time, or often we'll just say divided by time, meaning the change in time. So if we go back to the example with Mr. Bolt, okay, we know he completed the 100-meter dash in 9.58 seconds. We also know that he started the race at a speed of 0 meters per second. And after a little bit of careful research, it seems like his top speed during that particular race was 12.22 meters per second. And that happened about between 60 and 80 meters of the way through the race. So I'm just going to say that's 6 seconds after the race started. So if we're going to calculate, we got to get a change in velocity. Anytime you have a change in something, it's the final value minus the initial value. So if we take the final value of 12.22 meters per second, subtract the initial value of 0, we can see that the change was 12.22 meters per second. And if we plug that in for our change in velocity, for the time it took to change the velocity, that was 6 seconds that it took to change the velocity by that much, then we can see that the average acceleration of Mr. Bolt was 2.04 meters per second, or we could say 2.04 meters per second squared. So that means that during the first 6 seconds, on average, every second he was speeding up by 2 meters per second. So he's going 0 meters per second, then 2 meters per second, then 4 meters per second, 6 meters per second, 8 meters per second, 10 meters per second, and then finally 12 meters per second at the end of his speeding up time. Now in reality, Mr. Bolt probably sped up a lot faster at the very beginning and then slowly gained up to that top speed the last 20 or 30 meters of that speeding up period. But in this course, we will only really carefully analyze situations where the object is experiencing uniform acceleration, meaning it's accelerating at the same rate the whole time. And that will make our calculations much simpler and doable with the equations that we have. Now, if you were to want to actually go on and measure how the acceleration was changing, in other words, you're like, ooh, I really want to get the rate of the change of position, because acceleration was the rate of the change of position, and now we want the rate of the change of position. There's actually a term for that. It's called jerk. No, really, it's called jerk. Not that you're a jerk for wanting to go there, but maybe the value itself is such a jerk because it's such a complicated idea to have a rate. Anyways, or maybe it's because when you change your acceleration, you're jerking around. Anyways, so I think that's the real reason that it was called a jerk. It's called jerk. Anyways, if you want to go into that, great. It's not part of our course, but knock yourself out. Enjoy learning physics wherever and however you can. One last word before we sign off here. Acceleration can be tricky to understand. I know the speedometer thing hopefully helps. How much are you changing your speedometer each second? But if you end up finding you're talking about velocity as though it was acceleration when you're asked about acceleration, you're not alone. Just make sure you back up and you think distance is how far you go. It's how much your position changes in one-dimensional motion. Speed or velocity is how much your position changes each second. Okay? And then acceleration is how much your speed or velocity changes each second. Okay? So I guess for you, I should be going this way. I'm doing everything for me, but for you, the speedometer would go that way. Anyways, have fun trying to piece out and sort out in your brain what is a velocity and what is an acceleration, and we'll catch you the next time on the scientific adventures of Beardman. Oh, and don't forget, if you enjoyed this, click that like and subscribe button. If not, let me know how I can improve it. I'll talk to you later.